Polymers are very common in the natural world. They are what makes up your skin. They are what makes up bark on trees. However, those are not the type of polymers we're going to be talking about today. The polymers we're going to be talking about in this screencast are all synthetic. These synthetic polymers have been around since 1910, and today the issues we are going to address listed here are how polymers are synthesized, how they can be categorized, the general structural and chemical characteristics of polymers, and how those affect the mechanical properties. Also, what are some common polymers and how they are used. What is a polymer? A polymer is a long chain of 1D covalently bonded molecules. So the polymer molecule is 1D covalently bonded chain. Listed here are three common polymers. We've got polyethylene, polyvinyl chloride, and polypropylene. Notice in their structure they are very similar. Here are all their chains. The only difference is one of these substituents on one of the carbon atoms is different. This will be talked about in a future slide. Polyethylene is right here, is used to make things like milk containers. Polyvinyl chloride, PVC, is used to make pipes for plumbing, and polypropylene is used to make ropes. As stated previously, a polymer is a long chain of 1D covalently bonded molecules. As shown here, here's two different polymer chains. However, we never mentioned that between the polymer chains we have van der Waals bonds between the chains, as shown here. Now, if you look over here at this diagram, we see what a polymer chain could actually look like. It is loosely coiled and it's very string-like. So why does it do that? It's because the carbon-carbon single bonds rotate. They rotate to make angles of 109 degrees. And there's a lot of ways in 3D space, as shown by this diagram here, to make a bond angle of 109 degrees, which explains the coiling. In order to better be able to talk about polymers with other people that know about polymers, we need a common vocabulary bank in order to describe polymer chemistry and just form. So, some of these important terms and concepts are monomer, mer, polymer, and degree of polymerization. Now, the monomer is the small, unreacted single molecule for the polymer. As an example, we have ethylene here. Ethylene here is shown in the ball and stick model and the Lewis structure here. It is again shown here as a monomer. It is again shown in monomer form here and here, right about to be reacted. Now the mer is different from the monomer, and it is the single repeat unit of the polymer. Shown over here, we've got two mer units of polyethylene right there and right there. Again, this is the mer, shown twice, right there and right there. And notice it is similar to the monomer, but not the same, because the monomer has a double bond between these two carbons, and the mer has a single bond because it has already been reacted. So there is a difference. Remember it well. Now, the polymer, as stated previously, is the entire chain. So we're referring to the entire chain when we talk about the polymer. The next term is the degree of polymerization. It is abbreviated as a lowercase n, and it is a measure of the number of mer units per polymer molecule. It is also found by dividing the molecular weight of the polymer molecule by the molecular weight of the mer molecule. So now that we know about degree of polymerization, I'm going to show you a common shorthand for the entire polymer chain. So here we go. We have our ethylene mer right here, and we can express the entire chain if we know the degree of polymerization by putting the mer in parentheses and having the degree of polymerization down here. Again, it's abbreviated as a lowercase n, and it'd be shown right there. So let's do a sample calculation using the degree of polymerization, or n, as 10,000 and the given mer. So and let's try to calculate the molecular weight of the entire polymer chain. So we can see from this equation again, we can rearrange it and see that the molecular weight of the chain, so the entire polymer chain, is equal to N times the molecular weight of the mer. So we already have N, that was given to us, and so now all we need to do is calculate the molecular weight of the mer. And this is done by looking at a periodic table and figuring out what 2 carbons plus 4 hydrogen would end up being. So carbon is 12, so we got 12, 12, and then hydrogen is 1, so 1, 1, 1, 1, giving us 28 grams per mole for our molecular weight of the mer. And now we know, given that our N is going to be 10,000, we can find the molecular weight of the chain by multiplying the two together. So that's 10,000 times the 28 grams per mole. So the molecular weight of the chain is going to be equal to 280,000 grams per mole. We just did a sample calculation of the polymer molecular weight. So how does that polymer molecular weight affect other properties? So let's find out. First, we're going to outline what are the similarities and differences of candles and plastic milk containers. So right down here we have a table that lists the differences of the candle and the milk container. Now the candle is made of paraffin and the container is made of polyethylene. Notice that their degree of polymerization and therefore their molecular weight is different. The candles has a lower molecular weight than that of the polyethylene. So what is interesting though is that these two types of materials, the paraffin and the polyethylene, they have the same mer, which is ethylene, the ethylene mer as I have been using in the other examples. So this guy right here. So they have the same mer, their degree of polymerization is different. That N down here would be different. So also notice that their molecular weight for the entire chains, this is talking about the entire chains here, is less for the candle than for the container. Also, the chain length for the candle made of paraffin is less than the container made of polyethylene. So, looking at the trends in this table, we can maybe sort of kind of predict that the melting temperature would also be less for the candle than for the polyethylene. So let's go to this graph up here and figure it out. This is a graph that has temperature in degrees Celsius on the y-axis and the number of carbon on the x-axis, and plotted is the melting point in degrees Celsius as a function of the number of carbons and the boiling point right here as a function of the number of carbons. So let's find what the melting point of this candle would be, because we know a degree of polymerization is given as 11. So we need to determine the number of carbons from the degree of polymerization. Now, the number of carbons is equal to the degree of polymerization, which is 11 times 2. The reason why it's times 2 is because in the mer we have 2 carbons. If there were 3 carbons in the mer, there'd be 3, etc. So we have 11 times 2 to find the number of carbons, and that would give us 22. So we go up to this graph. We've got 23 right here in the middle, and then 22 would be probably about here. Then we go up from the x-axis to the melting point curve, and then to find the melting temperature, we go from the melting point curve where it intersected to the y-axis over here. Right. So it'd be about there. Now we can tell it's under 50 because it's, a little under halfway between these two, but it's a little over halfway too, so it's between 25 and 50. We're going to call it 40 degrees Celsius. Now, in order to find the melting point of the polyethylene, we would need to have this graph stretch all the way out to 2 times 10,000, and and it just simply doesn't. So I will tell you that the melting point of polyethylene is 125 degrees Celsius, which we could have predicted because notice as the number of carbons increases, the melting point and boiling point also increases. Like, right, notice it's a positive correlation here and here. So the real question is, why does the melting temperature increase with more carbon atoms in the chain? So the reason why is because they have longer chains. And between those longer chains, we have more van der Waals bonds between the chains. Between the chains. And then, because we have more van der Waals bonding to overcome, our melting temperature increases. So there you have it. That is the end of our introduction to polymers. In the next few videos, we'll be talking about some different methods of making these polymer chains and some different classes of commonly used commercial polymers. Thanks so much for watching, and happy engineering!